Lost me. Too quick. It's not expecting energetic speakers.
Okay, so two small announcements. First one is, please don't be shy and add your questions and dreams to this brainstorming list that you got the link. Okay? If you don't want to sign, don't sign, but keep adding your questions so that we have a topic to discuss tomorrow after the colloquium of the current. Second announcement that today, there was here some discussion following the consensus. And so we propose to have an informal discussion at 2:30 about ongoing work on massless fibers. We are bootstrapping similar scattering algorithms. So, okay, if someone is interested, it's very, very preliminary. We don't have good results, good plot yet, but if you're interested in discussion at 2:30, okay, so let's continue with the talk, which should probably be the first talk on the list. So finally, we'll learn what is an S-matrix.
They don't hear that. So, it's a loud microphone. Thanks for inviting me here. It's really a pleasure to be here and meet all of you. I think I'm sort of an outsider. So people who don't know who I am, I work on QCD mostly. That's sort of my day job, precision calculations, scattering amplitudes, resummation, things like that. But lately, I've been very much interested in the S-matrix, and I think there's some foundational questions about it, particularly in the context of theories of massless particles and gauge theories, that we really don't understand. I've spent a large part of my career studying infrared divergences, and this talk will be kind of trying to give you different perspectives on the infrared divergences that appear in the S-matrix. So the basic idea of the talk is to try to understand a little bit better what this object is that we're all spending our time studying and calculating. And the take-home lesson is going to be that this S-matrix is not some kind of sacred object, some God-given thing that has all these beautiful properties, but that we need to maybe adapt and modify it depending on what we're trying to calculate. So that might be disappointing to a lot of you that hoped it was sort of a well-defined starting point for rigorous mathematical investigation, and I maybe try to convince you that it's not so rigorous. So this is based on 2 papers, but sort of a lot of other stuff that goes into it. These are just various grad students and undergraduates that I've been working with on this. So to begin, let's just think about what we intuitively mean by the S-matrix. So you have some particles coming in, and some kind of scattering, and some particles coming out. And we kind of expect to call this some kind of in-state and some kind of out-state. And what you expect is that we're interested in the sort of amplitude between the out-state and the in-state with this sort of, we'd have minus I ht with the Hamiltonian acting on in, and then you would want to take the limit as t goes to infinity and call this some sort of S-matrix element. And I'll put a question mark there. And this is intuitively what we said. You start with some in-state, you set up your system, and you evolve it with time, and then out comes something else. Unfortunately, this thing doesn't actually make any sense. It is not what you calculate, even though many people think this is what we mean by the S-matrix. A way to see that is, well, first of all, we have to say what we mean by the in and the out states. A natural thing to try to guess for what the in and the out states are just eigenstates of the Hamiltonian, something of given energy. So suppose this is some E in, I in, and then we would have our out state be some other state. And of course, since energy should be conserved, the E out should be the same as E in. But in any case, this would give us that this matrix element we would calculate the limit t goes to infinity of essentially e to the minus 2I E out t times, kind of delta in out, whatever that matrix element. Well, I don't know. There's one energy on this side and one on that side. You can drop the two. It's just, I'm taking an energy, I can sit over here. Oh, right. Put one. It doesn't make any sense either way, right? So this is not what we mean by it. And this may seem like a sort of trivial problem with the S matrix, but actually this is really fundamental. And I think whatever we mean by the S matrix, it is not that we're just starting with some state of well-defined energy where we know what the particles are and we know what the state is, and we're evolving it with time and then projecting on some other states. That is not what we're doing. So we need a modification of this definition that corresponds to something more in line with what we want and should have non-trivial properties. So it's not just the identity times some infinitely oscillating phase. So a place to get started might be to look at classical scattering. Right, so we have, I don't know, a planet and something comes in and goes around it. Something like this. And here you imagine, so we have non-trivial scattering, we have something coming in and a different thing comes out, which is obviously different from this, which tells you that the same thing comes in and out because they're eigenstates of the Hamiltonian. So what do we really mean by this? What we think is that we're starting with something with a given incoming momentum, and it comes out with some outgoing momentum, which is different. But really what we mean by this is not that this momentum, this is again something that has constant velocity or constant momentum. So what we're doing is we're kind of projecting from the true trajectory of this onto a straight line. We're saying that sort of asymptotically it goes straight, and then asymptotically over here it goes straight. And what we're really doing is somehow jumping from this exact trajectory onto these straight line trajectories. And it's critical that you make that jump, because if you don't make the jump, again, you get something, you're just starting with the energy and you end up with the same state that you started with, and nothing ever happens. This is true even classically. In quantum mechanics, we do the same thing, but here we do scattering of plane waves. So this comes in, and outgoing plane wave is a little bit different. So we have the true scattering states. We would have some exact eigenstate, which is not a plane wave, psi in, say. And we're approximating it with e to the I px. And then we're projecting on something else, which is e to the I pfx. And again, there's this exact solution where nothing ever changes, just the state evolves with time according to the Schrodinger equation. And somehow we're jumping from this exact trajectory onto a kind of a free trajectory, which is critical to giving something non-trivial in the definition of the S matrix. Otherwise, you just get one and nothing ever happens. So this is essential to make the S matrix interesting.
Why aren't you talking about wave packets?
Right. So you can talk about wave packets, right? But in the end, what we take is the wave packet, and we take a limit where the wave packet approaches a plane wave. So that's essential to the derivation of a lot of these things, especially in quantum field theory. Yeah. Well, so you don't need that in quantum mechanics. If you have a localized potential, you don't need to take the wave packet picture. But you do in quantum field theory. Well, yeah. Right. So let me come back to that. It's not really the main point I'm getting at here. So what do we say here? We have this sort of exact state, and we have this incoming state, which is this plane wave state, and we have some other state which is close to it but not exactly the same. And what we want is for these things to approach each other at asymptotically early times, and then there's some sort of psi out, which also approaches the same state. So I'm calling psi the thing that evolves with a full Hamiltonian, and then in and out are the things that evolve with free Hamiltonians. And you expect that this should match onto that at early times, and this should match onto that at late times. So what we write more precisely is we want the limit as t goes to infinity, e to the minus I ht of the fully evolving state, evolves with a full Hamiltonian, to be equal to the limit as t goes to infinity, e to the minus I h naught t times psi in, the psi out at infinity. And we want limit as t goes to minus infinity, e to the minus I ht psi of the same state to be right? So part of the problem is that neither of these states actually exist, that this limit doesn't exist because of, again, this is some oscillating phase, and so you don't end up with a well-defined a state. But this is sort of physically what we mean, and there's ways to make this more precise. What we really do is we move one of these operators onto the other side, and so we say that psi is given by this molar operator acting on the outstate, where this molar operator is omega plus is limit as t goes to infinity e to the iht minus I at 0t, right? And you can make this precise. So what you want to say is that the difference between these two states approaches 0. You can integrate it in quantum mechanics and make sense out of it. So these molar operators play an essential role in the conventional definition of the S matrix, at least in quantum mechanics. And in particular, what we do is we define so we write psi out is omega plus dagger psi in, which we write as, psi of the fully evolving state, which we write as omega plus dagger psi minus psi in, and we call this the S matrix. So there's a sense in which the S matrix really does map these in states to these out states, but the in states and out states you should think of as the things evolving with the free Hamiltonian. So I find it helpful to draw this picture where we would have an in state evolving with the free Hamiltonian to some state in infinity, and then it evolves back with a non-trivial evolution to some state psi, and then we evolve that to infinity. Which way did I put infinity? Infinity is, so this is minus infinity. I guess this is all backwards. And this would be psi out. So this is, you know what? Sorry, it's a little unintuitive. But the point is, so the S matrix maps this state to this state through this intermediate state evolving with the full Hamiltonian. So it's a little weird, and what I'm getting at is that this is essential in the definition of the S matrix to have this funny business, otherwise you just get one, and the whole thing is trivial. Roughly speaking, this S matrix, so you think of these molar operators as roughly e to the I h interaction t, where the interacting Hamiltonian is the difference between the free Hamiltonian and the full Hamiltonian. So roughly speaking, the S matrix is defined this way in the interaction picture, where you factor out the free evolution, and the S matrix tells you the non-free evolution. So this is the conventional way it's defined, and this works fine in quantum mechanics, at least in cases with a well-defined localized potential. It doesn't work in quantum field theory, and there's a few problems with this. There's some problems with this definition in terms of the molar operator are, one, the interaction picture doesn't exist. So this is Harks Theorem. Well, again, the gist of the proof is that these asymptotic states don't exist. So you can't construct these things formally. What? So.
Whatever, can you give us the germ? Because otherwise it seems apodictic.
So you can't prove the existence of these states. So let's talk later. It's not essential. It's complicated, and I'm not even sure that it's that important. But if you read books on the S matrix, this is sort of a fact that destroys it. And so, in fact, this is not the S matrix that's used when you derive rigorously what it is. So the LSE reduction theorem, for example, avoids the interaction picture because of Harks theorem, and instead works completely in the Heisenberg picture. So there's a non-perturbative definition in the Heisenberg picture.
Can you please say why the Harks theorem applies to the theorem of the quantum mechanics?
Yeah, because of infinities. So you have order by order, you have singularities, and you have non-normalizable states that appear order by order. I can go through some specific examples and work through the details of this. Yeah, I want to sort of get to the new stuff, so let me not spend too much time on something that I don't really care about. So the non-perturbative definition, this is in the LSE reduction theorem, which uses the Whiteman axioms and so on. So it assumes a mass gap, it assumes a unique vacuum, it assumes a lot of things that don't necessarily apply in.
Sorry, but you're saying to the whole audience that the main problem is that the S matrix does not exist because of the Harks theorem?
No, I'm not saying that. Hold on. The main problem to the audience is, Ricardo, hold on. The main message here is that it's not what you think, which is you start with an energy eigenstate, you evaluate with time. Right. So this is the definition. This interaction picture construction with the molar operators is what we use. This works in perturbation theory. When we calculate the S matrix in perturbation theory, we're just working order by order in some perturbative coupling and evaluating this thing. And that's what we actually do. But if you try to rigorously define it, there's two approaches. One is this rigorous LSZ reduction theorem with wave packets and so on, which is a different approach. And then the way that we actually calculate things in perturbation theory uses the perturbative expansion of this in the interaction picture with Feynman rules.
My suspicion, and it could be completely wrong, out of my knowledge, and I know the subtle perspective there, could it be that the main hypothesis of Harks theorem is that the split between H0 and Hi in H is assuming that Hi is associated to a local random. It's local. I mean, if you make that assumption, then I believe that there's no interaction picture. But if you allow non-locality in the interaction part, and then the split is very non-trivial. So
that may be true. I don't know. Okay. Okay. In any case, even in this non-perturbative construction with LSZ, the point is that Ricardo, hold on. No, you can't ask. No last things. The non-perturbative definition, the things that you scatter are not energy eigenstates, right? They're these wave packet constructions. But again, even in this non-perturbative thing, if you tried to evolve with time a full energy eigenstate, you would get nothing. You would get something trivial. And so they use, there's a wave packet construction that's implicit in this. And I think whenever we're doing anything with the S matrix, we should make sure we know what the things are that we're scattering and figure out which of these pictures it maps into. In any case, that's not what I'm talking about today. But I just wanted to get the basic concepts on here. On the board, the thing that I'm interested in is in real theories like QED or the standard model, or any theory with massless particles, you end up with S matrix elements are divergent. So you get things like 1 over epsilon squared and so on, which are infinite, order by order in perturbation theory. So it doesn't exist because the S matrix is infinite. On the other hand, you can also exponentiate these things. You end up with something like e to the minus 1 over x e squared, which is 0. So we have the problem that this thing doesn't exist, and moreover, if you try to calculate it, it's either infinite or 0 at any order in perturbation theory.
I mean, the first line just doesn't work, right? Because your perturbation theory, like,
yeah, right. And but the second line also makes it trivial. So I mean, I mean, being a little facetious here, it's not really a limiting factor because we know how to deal with these things in many ways. But formally, if you tried to do, say, a non-perturbative calculation of the S matrix in QED, you wouldn't even know where to get started because it doesn't exist. So realistic theories violate the assumptions that are used to derive it, the Whiteman axioms, there's no mass gap, and so on. And so we can't even get started on thinking about non-perturbative computations in QED. And that's sort of what I want to address, that maybe there's a better way to do it. So let me first just briefly discuss some solutions to the infrared divergence problem of the S matrix. So one is what we call the cross-section method, which is probably the one you're most familiar with. Right? So this says IR divergences cancel when we integrate over phase space. So we do integrals d pi of this matrix element squared. We should get something finite. And this is what we do in practice. They say, well, the S matrix itself isn't physical, but cross-section is just physical, which are S matrix elements squared, and things should cancel. And there's plenty of evidence that this works, and essentially all physical processes we've seen, and this is the power of the predictivity of of quantum field theory with massless particles. There's some history to proving that this actually works. So there's the Bloch-Nortec theorem. I assume most people have heard of these things, but just wanted to remind you what they are. This is actually quite old. This is from 1937, which says that IR divergences cancel in QED if we include all outgoing photons. So the Bloch-Nortec theorem is particular to QED where the electron is massive and you have an abelian theory. It uses critically abelian exponentiation to prove that this works. It's a very different language when it was discussed, but it's not a very general theorem. It doesn't apply in QCD, for example. A more general theorem is the Kln Theorem, and this is from 1963, which says that you have to include all initial and final states in an energy window. In an energy window. Right, so something like the way they write it is, let's see, the initial state has some D of E is some domain. The final state also is some states of energy, and you sum over the matrix elements squared for this transition. So again, if you have QCD and you're scattering gluons, if you sum over some window of gluons within energy in some window, some compact window on the given energy, and also final states, right? This is not something we normally do. This means that if you're scattering, glue to glue, you also have to include 3 incoming gluons and 3 outgoing gluons and 6 incoming gluons and anything that is possible in the energy window. And the energy window is a nice way to formulate it because it includes both sources of infrared divergences and massless theories, collinear, which are also known as mass singularities, and infrared divergences. Yeah. Yes, right. So all I'm saying is that the cross-section method says that these things should be finite. There's other clauses, and there's a lot of reason we're interested in the S matrix as an amplitude. But it is infrared divergent, and we have to be careful about that to try to make physical interpretations. So this is a theorem. It's funny that a lot of people know about this theorem, but I haven't met anyone who actually went through the proof of it. And it turns out, if you think about it just for a minute, it's sort of stupid to say that you need to take this energy window because energy is conserved. And so if I just fix the energy of the initial state, all the final states will automatically have that energy. I should say both of these work order by order in perturbation theory. They're not non-perturbative statements. They're perturbative statements. So this Kln theorem is actually weaker than you need. You can make a stronger statement that's more restrictive. And this was the content of one of the paper from last year. Let me go back to the start here. So what we showed is that, in fact, you don't need to sum over initial and final states. So we showed that you can include all F or all I. I don't want to say this. And it's also true that the finite parts vanish. So not only the IR divergences cancel, finite parts cancel too. Which makes it all kind of stupid. But this is the same is true about the Kln theorem. What they showed is that the amplitude is actually 0. And the proof of this is really trivial. The proof of this is that the cross-section of some initial state going to anything is 1. So the probability, if I start with a given state, the probability that evolves into anything is 1 because of unitarity. And 1 is 0 to all orders in perturbation theory. Right? And the same is true that the cross-section of anything going into some final state is 1. Right? And this is 1 plus 0 times g plus 0 times g to the 4th, and so on. Right? So essentially, this is all that there is in the Kln theorem, is this stupid statement that unitarity. And they write it in this very complicated way. But the much simpler way to say it is just the cross-section is 0 the cross-section is trivially 1. It actually has a lot of really interesting implications, because one thing you have to include for this to work is that the final states that you sum over have to include the initial state. So you can't avoid the forward scattering region. And the forward scattering region is very singular, and it's very hard to compute things because you end up with products of distributions and stuff like that. But it's essential to any explicit checks of the Kln theorem and also explicit checks of this proof. There's a question. Yes.
In Weinberg's book, he says, following sentence, he proved the Kln theorem, and then he says, he showed electrodynamics that it works by summing over a final state without need of summing over the initial state. And then he said, it's funny that you don't need to sum over the initial state. So I think he has the proof with summing only.
Right, but you can also sum over initial states if you want. Weinberg's proof is very, Ryan has a couple of, yeah. So,
I thought that
Weinberg, right.
Original paper, but I read it in
If you're worrying about like the chapter 19 of Weinberg where he talks about infrared divergence, it's all in QED. What he's doing is reproducing the Bloch-Nortec theorem, not the more general thing that applies in non-abelian theories. Right, and that's the case.
We're not thinking about the in 1963.
Right, what they were thinking about is, what? No, but they were thinking about pion decay. So even in QED, they were thinking about the massless limits. They were interested in collinear singularities. So they were interested in something like a pion decaying to an electron, and they wanted to know when, as the electron mass goes to 0, you get a finite answer.
But I think, so you think that what Weinberg says does not apply to pions?
It doesn't apply to the mass singularities. It doesn't apply to massless charged particles. Right. I'm quite sure of this. So let me just give you a non-trivial example to say that this is actually kind of interesting. So consider photon scattering. So we could have in QED these kind of diagrams. So this is gamma gamma to E plus E minus, and you would have, of course, the cross diagram. Draw it like this. So you sum these and you square them, and you integrate over. So let me integrate this over phase space for the outgoing electrons, and you get something like E squared over pi Q squared minus 1 over epsilon plus some constant, whatever it is. Right? So this is an infrared divergent at tree level. And we have other examples of this. So there's a mass singularity associated with this particle being massless that's present already at tree level. Compton scattering is also this well-known infrared singularity. The question is, what would cancel this, right? So normally you say, oh, well, I know that when we have phase-space singularities, they're canceled by loops. But here, if you had a loop, it would be higher order in perturbation theory, so that can't cancel it. Turns out what cancels this is this diagram, which is the interference between the tree level forward scattering and the box diagram plus the crossings. And if you evaluate these, you get E squared over pi Q squared times plus 1 over epsilon minus 1. Right? So the point is that this process, E plus E minus, and this process, gamma gamma to gamma gamma, are not separate processes. They have to be included if you want to talk about something physical. And this should be maybe a little shopping. It was confusing to us when we started thinking about this, because you think, well, I'm scattering photons in QED, right? I shouldn't care if there's electrons. I should have a well-defined cross-section. Just say photons come in, I bang some lasers together, light comes out. I just see if I have any charged particles, right? So you'd think that the cross-section for photon scattering to photons is well-defined on its own. But this says that it isn't, that you have to include also electron-positron states in your final state in order to get something that exists. In the massless electron, right, to cancel the mass singularities, right? I mean, more generally, there's if you consider E plus E minus to Z, say, so you have all kinds of diagrams like this, cross this, but then you have these kind of diagrams with incoming a photon scattering off a leg interfered with these disconnected diagrams. So we don't normally deal with disconnected diagrams, but they're actually essential to proving infrared divergence cancellation according to the Kln theorem or our generalization. And it's actually quite interesting to explore the examples and work out these cross-sections, because calculating disconnected diagrams it involves technology that you're not used to, involving these weird distributions and extra singularities. But it can be done, and you can check these things explicitly. And in our paper, we give a number of examples.
From what region of phase space is when they...
This is all just totally inclusive. What region is associated with it?
With
in this case? Yeah. So it's the region where essentially there's a collinear singularity. So the photon goes, you can see here, so the photon goes forward, right? So you can't tell the photons going forward from electron-positrons going forward. And one way to think about that more physically is you can think of a photon splitting into an electron-positron pair and say one of the electrons goes this way, well, I could have that split where they go in the same direction, right? And so this one has charged particles and that doesn't, and these interfere. These are degenerate states. Or one of the electrons can basically have zero energy, and a photon can directly turn into an electron and a zero energy electron, and that looks like it changed the charge. And this only happens when you have no mass. So when you think about it a little bit, it's not so strange, but it is important. It's important to keep in mind. Okay. What I want to talk about is not so much this cancellation, which I think is interesting, but again, all you do is get 0 at each order, so it doesn't tell you much about physical things that are non-zero. So that was this sort of cross-section method approach. The second approach that's discussed in literature is more aimed at getting finite amplitudes. So the second approach is called the coherent state approach. So this is people like Chung, Fatty of Coolidge. There's a whole history of this. Basically, from the 60s onward, every 5 years, someone writes a paper about it. Most of them don't make any sense, but then you can synthesize some coherent story from the literature. And the idea here is to move the IR divergence from S to the states, right? So what you do, for example, in QED is you define a dress state as the exponential of some factor times the bare electron state. So this would be a dressed electron, and this is kind of like a Wilson line acting on the particle. There's some explicit formula you can find in some of these papers, which is the integral times P mu over P dot K. So the soft factor times the polarization factor. And then there's some phase here. And then AP dagger, ... Something like that. So essentially it takes the full interaction and just takes the soft limit of it and then adds that into the state. So you can think of this state as being kind of an electron plus kind of the dress state, which I can write as this, kind of a bare electron plus a photon plus multiple photons. And they all come from the exponentization of this creation operator acting on the vacuum. So it's creating a bunch of photons. The way this is formulated, it's not obvious that momentum is conserved because you can create photons of arbitrary energy from the same state. So these dress states don't have well-defined, they're not momentum eigenstates. They don't have well-defined quantum numbers under the momentum operator, and that makes them a little hard to work with. They also have these integrals, which are infrared divergent. So they're not actually, there's no Fock space for dress states. So there's a lot of problems with them. But they do work informally in making the matrix element finite in the sense that, so if I think about something that would normally have an infrared divergence, so if I think about, so this would be, say, Z to E plus E minus dressed. So normally you would get a loop correction, and this would be infrared divergent. So what this does is it takes this loop and adds to it corrections involving essentially photons coming out of this leg. You can draw them like that, and then the ones over here, and then this whole sum is finite. Right? So what's happening is the infrared divergence from the loop is being canceled from real emissions associated with this Wilson line acting on the state, so that produces extra photons, and then they interact with a normal interaction with the leg. Yeah, so you'd have to put some cutoff in here, and then you end up with cutoff dependence, and so it really just moves the problem. It just moves the integral to here, and you end up with something that's also very hard to interpret. Moreover, no one ever actually computed these things. Let me just sort of say in words some problems with this. So no one computed it. You need cutoffs. But the main objection I have is that there's not a well-defined mathematics of these dress states because they're infrared divergent, so they're not normalizable states. They involve an infinite number of states. They're not momentum eigenstates. It doesn't really seem to solve the problem of infrared divergences. It just moves it from something that we cancel at the cross-section level to something at the amplitude level, but involving a sort of an algebra that's nonsensical. But the literature is also very confusing because people, they show formally that the IR divergences cancel and then stop, and it's not clear what it's good for, and no one calculates it. Okay. So what I want to talk about for the rest of the talk is the third approach. The third approach is kind of a hybrid. Let me put this back. Solutions to the IR divergence. So the third approach is to redefine S. So before we defined it as in terms of these molar operators, right, or omega limit t went to infinity, e to the minus I ht, e to the I a 0t, plus or minus infinity. So let's define it instead in terms of some other molar operators. I'm going to call these hard operators. Where omega plus or minus hard is given by the limit as t goes to infinity of e to the minus I ht e to the I h asymptotic t. So it's basically the same definition, it's just you replace the free evolution with some kind of asymptotic evolution, right? And so the idea here is, again, we have, suppose we're scattering two electrons.
Let me ask you a quick question.
Yeah.
Isn't your hard omega related to the full omega by the r to the rt operator?
So there's a relation between the two, but it's not so simple. So first of all, this only works for soft divergences, not mass singularities, not collinear divergences. So this is special to QED, essentially. I'll explain the connection in a minute. But let's just sort of say the physics of this redefining the S matrix approach. The idea is that even if we're taking the electron and positron far away from the scattering region, they're never free because there's still long distance interactions, Coulomb interactions, or more general types of interactions, right? Or I could have, photons. Nothing prevents me from an asymptotic electron from emitting a collinear a photon. So you can never separate. You can never isolate the asymptotic states, right? So we have this physical picture that far away from the interaction, the particles are free. That's just not true in theories of massless particles because you always have long-distance interactions, right? And therefore, what we should do is not use the free Hamiltonian, since that's never an appropriate description of the physics. We should use some asymptotic Hamiltonian that correctly encapsulates something having to do with the asymptotic behavior of the initial state by itself or the final state by itself. So that's the idea, but then the question is, how do we choose the asymptotic Hamiltonian? There's properties we want it to have. Well, the main thing is that we want the IR divergences to cancel in the matrix elements of the hard S matrix. But you can do that sort of trivially. So one thing I can do is choose J asymptotic to be H, right? And if I did that, then S would just be 1, and everything would be trivial. Right? So that's throwing out too much. We don't want to do as much as setting H asymptotic equal to H. So essentially what we want to be able to do is separate out the asymptotic interactions from the hard scattering. So it turns out that's possible because of unique theories of, at least in gauge theories, because of factorization. So factorization tells us that the infrared divergences are due to the sort of universal evolution of the states. So if you had a process like this in QED, right, I might have outgoing gluons and so on, and I might have soft and things like this. It turns out in QED, this kind of matrix element can be written as a product of a hard function, which might be a function of some hard Mandelstam variables or whatever it would have, times a soft factor, which can be written as a product of a matrix element of Wilson lines, times various collinear factors. Which you can also write in terms of fields and Wilson lines in various ways. Right? So this is a soft factor, and these are collinear factors. And this factorization, which is known to hold to all orders in perturbation theory for scattering amplitudes in QCD at least, in gauge theories, tells you that this this object, this is sort of the hard part. hard, let me write hard kernel. Right? So really what we're doing here, this is kind of just scattering, kind of a contact interaction that just involves the large directions of momentum flow. This thing involves just Wilson lines, so you don't have any of the hard interaction at all, and it involves corrections involving long distance interactions. So these kind of Coulomb gluons you might exchange, or Coulomb photons, come out of this factor, and these things involve these collinear branchings. And so the point of view here is that this kind of evolution, both of these factors are independent of what actually happens in the scattering. They're universal. So you can calculate these once and for all for the evolution of the asymptotic states. And then the hard scattering tells you that it has to do with the process you're interested in. And the separation suggests that we should be able to define the asymptotic Hamiltonian as just accounting for these kind of interactions. And there's a very precise way to do that. So how are we doing on time? 5 minutes, okay.
When I compute this asymptotic Hamiltonian, does not diverge anymore?
The Hamiltonian is a bunch of local interactions, right? So let me so there's the easiest way to write this down is using effective field theory techniques. So I'm going to define H asymptotic is the Hamiltonian of soft collinear effective theory, which has some form. It's basically there's soft gluons, and then there's a sum over collinear sectors of. So each sector has its own set of labels, and then you kind of factorize the interactions. Let me not write down the details. You won't understand it if you've never seen it before. Okay, so there's a way to define this precisely, and then you have to know how to calculate it. So there's actually some neat tricks that you can do to calculate this thing. So we're defining it this way in terms of these molar operators. So the first thing you might try to do is just do perturbation theory. Since we replaced H0 by H asymptotic, you say, well, instead of using free propagators, we should use propagators which are eigenstates of the asymptotic Hamiltonian, right? So if we had a way to compute these things, right, we'd end up with a propagator which is kind of, the full propagator should involve the full evolution of the asymptotic Hamiltonian. And that's impossible to compute. You never don't know in closed form. And it's also, we're doing things in perturbation theory, and there's couplings involved in this asymptotic Hamiltonian, so it doesn't make sense to try to do perturbation theory using the full propagator of the asymptotic Hamiltonian. So instead, what we do is we break apart the hard S matrix. We write it as e to the minus I t, let me write t plus as t goes to plus infinity, e to the I h t plus, e to the minus I h t minus, e to the plus I h asymptotic t minus. And let me insert in here e to the I h0 t, e to the minus I h0 t minus t plus. And I'm going to insert in here e to the I h0 t minus. The free Hamiltonian, the usual one. And so when I write it this way, this becomes a product of this and this, and then I have, it's just free gluons and free quarks, right? So the point is that this middle piece is just S, and then this thing is what? The whole construct, everything I'm doing is perturbative, right? It's all based on the interaction picture, which is perturbative. But S, so you can think about S non-perturbatively, right? So this definition, the original definition, this is some object that in principle you can compute, just like you do non-perturbative computations of the S matrix, how you define it.
But the interaction picture, let's say, doesn't exist, as you say, in quantum mechanics. When you do the separation, it's not perturbative, that separation. It don't work in perturbation theory, in the interaction Hamiltonian, when you derive the S matrix in quantum mechanics. The potential is localized, but you treat it perturbative.
That's right. So I don't know exactly how to do this construction non-perturbatively, but I believe it should exist. But it's an interesting question. Let me just sort of get the main point here. So there's a sort of asymptotic molar operator, and then there's another asymptotic molar operator here. right? So what we're doing here is we're inserting the free Hamiltonian. So this middle evolution is determined by the normal evolution with the full Hamiltonian and the free Hamiltonian. And then all of the Sket Hamiltonian, this crazy thing, goes on the ends and kind of goes from 0 to infinity. This is easiest to understand with a picture. So we have this idea that we have this in-state evolving with the asymptotic Hamiltonian. I don't know how to draw this. Let me draw it this way. So we have psi and psi out. So this is the asymptotic Hamiltonian, and this is the full Hamiltonian. This is the same picture I drew before, but before I used the free Hamiltonian, and now the evolution with the asymptotic Hamiltonian is non-trivial. But in any case, we're still mapping in-states to out-states. So when I insert these operators, what I'm really doing is projecting, going this way and then back out with H0 to some intermediate state, which I'm going to write psi d. And this is psi d prime, say. And so what you're doing is we're taking this part is the evolution with the asymptotic, and this part here is just the full S matrix. And then this other part is with omega minus, I guess, plus asymptotic. This is minus. So this is a little messy, but the idea is that you combine the computation of the first part with the asymptotic molar operator, which is essentially the evolution of the in-state to address state, all kind of at time t equals 0. And then what you're doing is you're scattering with the S matrix of the dress state into another dress state, and then evolving the dress state back to an out state. So these in and out states are just regular electrons, just Fock space normalizable elements of the S matrix, the normal things you would compute. And so the way to interpret this is that the asymptotic evolution dresses the state. And then you're calculating the scattering according to sort of like the coherent state approach of the dress states itself. But again, these things don't need to exist. They don't need to be elements of any Hilbert space. All that we require is that the matrix elements of this to this through the full hard S matrix are well defined, and you can do those computations. So it's a little tricky to work out the perturbation theory rules for this. You need to use time-ordered perturbation theory, not Lorentz invariant perturbation theory, because it evolves from 0 to minus infinity, not minus infinity to plus infinity. So you don't end up with delta function. Energy is not conserved. You end up with energy propagators, and it's a mess. But in the end of the day, everything works out, and the final result is Lorentz invariant, and you can calculate it for various cases.
So this is essentially, you're essentially using Sket, if I understand correctly, to generalize coherent state approach, because for the collinear emission not happen.
Well, so I don't think of it as part of this coherent state picture. The coherent states arise as intermediate states in the calculation. But I think it's very important to emphasize that the states that we're scattering are just few particle electron or photon or gluon states. Right? They're not dressed. They don't have infrared divergences in their construction. So they're normalizable, and you can think about scattering. And the dressing occurs in the sort of evolution to minus infinity and back, which is just sort of a mathematical artifact of the way we're doing the calculation. I think the dress state approach is confusing, and I think it doesn't actually solve a problem. This does solve a problem. And I should say it seems really complicated, but in fact, the result of all of this is that the diagrams are just 0. So if you use dimensional regularization, everything coming out of this theory is scaleless, because there's no scales associated with the asymptotic region. And so you just get 0 at all orders in perturbation theory. And so what that does is it essentially turns the UV divergences into IR divergences of the S matrix into UV divergences, and then those are removed with counter terms. So you end up just extracting, at least in MS bar, just the hard part, the finite part of the scattering matrix element. So I could give you some examples. I don't really have time, but so we computed this for a number of cases, like the C plus U minus Z and Drell-Yan and deep inelastic scattering and so on using this framework. One of the more interesting things is the connection to scattering amplitudes.
Sorry, can I ask you, at least
Yeah.
Harks scattering is the physical thing, this is the physical part.
Yeah, that's the claim, is that the matrix elements of SH are the physics of it, and everything else is sort of the universal infrared divergent part has to do with the definition of the things that you're scattering. But let me just write down.
Does it have a scale associated with it?
The what? Yeah, there'll be a scale, right? And that scale is essentially, so there's a normalization scale. So when you use
That is not physical. So the scale should, in order for this to be physical, the scale should be associated with something inobservable, some physical property of what you're looking at. Otherwise, this is not feasible.
Right. Well, I mean, the S matrix then has a scale a scale associated with the cutoff on the asymptotic states.
When you consider the cross-section of protons, there is a scale-dependent hard cross-section,
Yeah.
which is it has collinear divergences, which are cancelled by the dependencies by the PDF. Right?
That's right. So all of that goes through any physical thing you calculate.
Here you still have scale dependence at the end.
Not at the cross-section level. You do it at the amplitude level. But when you calculate a cross-section, that cancels. And you can show very generally that any
Saying that the cross-section you get from this
is identical, right? And it's sort of trivial to see because you just calculate these things squared, and this thing drops out. So you take the matrix. You're basically calculating some initial state SH. I'll put the final over there. Initial squared, and this ends up being F SH high. Well, for summing up for final states, let me write it the other way. SHF. Right, and then this sum, so then you write S as this sort of e to the.
So in this sense,
There's a cancellation that occurs, and the whole thing is just trivial because it's a unitary operator.
plus and minus, plus and minus.
What?
Let's say that I have QED and I want to compute the cross-section plus and minus, plus and minus.
Yeah.
What do I get?
Well, I don't have the explicit result, but I can tell you z to e plus e minus. Will that do? So you get the tree level. The tree level amplitude is exactly the same, and the correction is alpha 4 pi. So if I did the calculation, if I do this loop in QED, what I get is the tree level amplitude times there's an epsilon UV minus 2 over epsilon IR squared minus 4 over epsilon IR minus 8 plus pi squared over 6. When I do the calculation with the asymptotic Hamiltonian, I get additional diagrams having to do with this photon going into the asymptotic region. So normally these diagrams, this goes from minus infinity to infinity. Here we would have minus infinity. This is the hard interaction between the Z and the electron. The hard interactions are only in the QCD, in the full theory Lagrangian. They're not in the asymptotic Hamiltonian. So this interaction has to be before 0, but then I can have plus infinity here, and then I have to go back to 0. So if these lines go to 0, I can have additional interactions like that, or I can have cuts through them that look.
What does this match in the ordinary approach? Is this the total width?
Yeah, let me just write down the answer, and it should be a little clearer. So if I calculate the sum of these various asymptotic diagrams, I get alpha over 4 pi times 2 over epsilon IR minus 2 over epsilon UV. Right, so it's a scaleless integral. I've just artificially separated the UV and IR poles. So what happens is the IR divergences cancel between the full graph, and I end up with some renormalized, some UV divergences, but those are canceled by the renormalization. And so then what I get is that the matrix element of the hard scattering between the Z and E plus E minus is 1 plus alpha over 4 pi times minus 8 plus pi squared over 6. So again, if you did the calculation in full QED, you would get this kind of thing with all these divergences. If you do it with a hard matrix element, you just get a number, plus maybe some logs if you choose a different normalization scale. Here I chose the scale, so there might be a log of Q over mu. Right? But it's finite. So there's a scale. Yeah. But what? The matrix element. So if you calculate a cross section, yeah. So I can also calculate the amplitude for this to produce E plus E minus in a photon, and that thing is perfectly finite in any collinear limit. And if I sum those two, the mu dependence cancels. Anyway, there's sort of more to the story. It's so you can study this. We spent some time thinking about an n equals 4 super Yang-Mills, which is a theory where there's full of IR divergences, and people have all these different subtraction schemes to remove the IR divergences. Turns out that you can understand a lot of this about those results, about subtraction schemes that preserve Steinman relations and dual conformal invariants, all very kind of naturally in this language. So,
in other words, there's a scheme to compute exclusive processes and the price to pay that they depend on some factorization scale.
yes.
When you sum everything, then for inclusive for observables. Yeah, that's
Exactly, yeah. And the factorization scale is really the separation. It's kind of in the dress states what the cutoff would be, but we're doing it all in dim reg, so it's beautiful and it just becomes mu. But that's the physical interpretation of it. And this is, any calculation in soft linear effective theory has that kind of scale. All right, let me stop here because I'm over time and there's a lot here. So.
Just a question about the application. Can you compute something in gravity, like graviton scattering?
Sure. Yeah, again, it's very easy to do these calculations. You just take the full thing and drop the 1 over epsilon poles.
How difficult would it be? Just if you can give the level of difficulty of all these steps.
But again, it's you don't actually do anything because they're all scaleless integrals. So you do the full calculation in dim reg, and then you remove the poles, right? But it's a particular subtraction scheme. So what's nice is this operator is unitary, right? So if you want to separate, if you want to see the cancellation actually happen of the IR divergences, you have to not use dim reg, separate out the UV and IR, and then you can, you put a mass cutoff or gluon mass or off shellness or some crazy regulator. And these calculations are hard. We have a lot of examples where we do this. But if you just want to know the answer, you can just do it in dim reg, right? But so the issue is normally people say, let me calculate an amplitude in gravity, and there's IR divergences or super Yang-Mills. What do I do about that, right? And so they do things like take ratios of different amplitudes or different helicities, right? And they say, okay, well maybe this is the thing we want. But they say, oh, it looks like it exponentiates, or it looks like dual conformal invariance is broken in one loop. But if I subtract the exponential of the leading order result, then I cancel this dual conformal anomaly. Oh yeah, but then at 6-point amplitudes it's broken, and so I have to modify my subtraction. And it's sort of this sort of arbitrary set of rules because they're just doing subtractions. But if you think about it as not subtracting something in an ad hoc way, taking the ratio of 2 amplitudes, you just calculate 1 amplitude, then it's a much better organizing principle. You can exploit unitarity because this operator is unitary, and you can learn things. I mean, that's the sort of hope that we're getting at, is that it's a more natural object compute that's naturally infrared finite, and so it should have interesting properties. I mean, one thing I'm interested in, I'd like to talk to people about, is the analytic properties of this thing, right? I think it's much more similar to the analytic properties of a mass gap theory, like a massive scalar, than massless theories, which have these branch cuts and actual singularities, and Landau equations are complicated. But massive theories are simpler, and you have square root singularities, and sort of the structures are simpler. And I think the structures of this should be simpler too, and it would be interesting to understand what they are. And I haven't spent much time thinking about that, but
would you hope that non-perturbatively the structure might be the same analytic structure if you compute something here in perturbation theory?
Yeah, I'd love to look into that and figure out what it is. I'm not sure how to sort of get a handle on it, but I think it's worth thinking about.
Thank you very much.
Yeah.
It's just, I mean, maybe it's basically the same question, but now with this observable, I mean, analyticity, it will come at the perturbative level. It will come just from Feynman diagram in the same way, right? So,
right.
Like all, with the analytic structure of Feynman diagrams that we expect.
Yeah.
And the unitarity, you say that now this amplitude depends on this extra scale, but you can still write a unitary equation like the standard S matrix.
Well, again, it should be the S matrix is the hard S matrix is going to be. I mean, there's a scale that appears order by order, right? But we know things cancel because we have a normalization group invariance. So there's things you can calculate that replace the arbitrariness of the scale with some physical scales. I mean, I know how to calculate certain things in perturbation theory. I don't know how to study it non-perturbatively. I'm not sure if that answers your question. The point is, if you wanted to study the S matrix non-perturbatively in like n equals 4 super millions, how do you even get started, right? At least here we have a place to begin, right? Because that thing just certainly doesn't exist. It's infinite and zero and doesn't have any properties. So, there's a huge industry of people trying to study scattering amplitudes, looking for interesting properties, and there's no way to get beyond perturbation theory. This is, at least offers that hope. But right now it's a hope.
I mean, I thought that there was some physics in this zero, right? That if you ask for the probability of getting 2 electrons scattering to 2 electrons, and you have infinite precision to look for all the soft photons, you will always find some soft photons.
Yeah.
So it's just zero probability.
He has the way to do.
So
he can also
scale.
That's like taking mu very small, right?
Yeah.
So there's a sort of mu is kind of the cutoff on what we consider collinear or soft. and that's arbitrary. It's universal for any mu, right? And so we always have this separation, but you can certainly calculate, a hard S matrix between an arbitrarily collinear photon. It's just in the limit that that becomes exactly collinear, goes to 0, it doesn't blow up. Like these hard matrices have all the right soft and collinear limits to make it smooth, and so you can.
Here's a way to define amplitude, but do not contain any epsilon. So let me ask you, although it's a different thing, consider instead PP collision, like
Yeah.
there, which is clear. This is partly inspired by that, and you probably also did work, although I'm not following the literature. Somebody told me that you've done work. I refer to some guy on factorization.
I've done a lot of work.
I haven't followed. So, but this, a variant of this, isn't just what you need to prove factorization.
So you use
the arising of PDFs. I mean, because
so PDFs are separate, right? PDFs.
No, because in the case of hadrons, you will need, now you really have asymptotic states.
Yes.
They're massive. There's a gap. So let's say pi
Yeah.
mass. Let's say there are no photons. Okay, just for the sake of it.
Yes.
And then the quantity mu appears when you compute scattering, gluons and quarks. And then rather than simply summing it like this, you have to fold it.
But right, that's an
elements that give you, which will eventually, when square, will give you the PDF.
Right, that mu is an artifact of using PDFs. If you just calculated the scattering of protons, you wouldn't need mu. It is what it is.
But
yeah.
in perturbation theory, it's
right.
To do this factorization.
That's right.
So this can also be a similar formalism applied there, right?
Well, if you had a proton, you could evaluate PDFs and calculate their scattering in the same way. You don't need to redefine the S matrix. You can calculate the hard S matrix.
No, what I'm saying is that even there you can write SH.
Yeah.
In exactly the same way, but the mu dependence will not cancel until you fold it into PDFs. Right?
That's right.
That's
Okay.
Okay, one last question.
I have a very quick question. So this, when you mentioned that the dress state formalism had problems, I didn't quite catch exactly what the problem was. So maybe with this simple example, what would have gone wrong if I computed this matrix element with dress states instead of using this SH?
So dress states, first of all, people don't know how to write down actual expressions for them. In QED, they have this expression on the exponential.
In QED, yeah.
Yeah, but so QED, if the electron's massive, there's a kind of a sum over soft photons. But it's a UV divergent sum, right? There's no upper limit on the integration. So there's the same problem. If you put a cutoff in, that's equivalent to our mu. Moreover, those states aren't momentum eigenstates, right? They're also infrared divergent, so they're not elements of any Hilbert space, right? They have one over epsilons in the perturbative expansion in terms of normalizable states. So they're not normalizable. They're not well defined, right? And the prescription just talks about the singularity. Nobody actually explicitly calculates them. And when you have massless particles, people don't know how to construct the dress state. So it's only for soft singularities, not for collinear singularities. So they don't know how to do it for QCD. They only know it for QED. And QED, it's sort of a solved problem through Bloch-Nortzic. So it's not that interesting.
Okay, thanks.
Okay.
Yeah, I'm sorry, I went over.
Careful, you still have it here.
You want to start writing?
Yeah, sure. Test. Okay. Is that okay, like so? Or?
I think it's working, yeah.
Okay.
Okay.
1 second.
Did people get an email with a link for shared Google Docs to Weinberg? So only you. Sorry. I will personally send it to you.
Discussion on finance will be in room 3.
Yeah.
Yeah, room 3 per floor.
Okay, so let's continue. So just an announcement, actually the discussion won't be here. So if you are interested, the discussion on finance is going to be on the 3rd floor in room 3. Perfect. Okay. So let's continue with the same topic.
Yeah, okay, well, first thanks to the organizers for inviting me. And yeah, so the outline of my talk was essentially everything Matt already went through. Although I'm actually going to talk about dress states, and I hope that Matt's going to be happy after, or happier than he was before. So, right, I'll kind of try to cut down on the sort of things that have been said. But anyways, the thing I'm going to talk about is based on a work I put on the archive last year and kind of was inspired by some previous work with those people regarding infrared divergences. And of course, the question here again is, what happens if we want to scatter massless particles? What's a good description for it? Initially, the question sort of arose of the problem how to quantify information transport and scattering. For this, we need an out-density matrix, and if there's massless particles in our scattering process, that requires us to know the S matrix, but as Matt already said, the S matrix for massless particles is kind of a tricky beast. I'm not going to talk about non-abelian gauge theories, but I'm essentially going to focus on QED, and you're invited to also think about gravity because the infrared structure for sufficiently low energy processes are essentially the same. Okay, so S matrix, what do we mean by scattering? And again, as already mentioned, the rough idea is there's some sort of like asymptotic region here in the past to the left, where we have some notion of sort of like states we can define and approximately define, and we know sort of how to measure, how to say these are like localized particles. And now if we want to define scattering, what we usually do is we take our states, we evolve them back in time with a free Hamiltonian, forward with sort of like a full Hamiltonian, and then again a bit back in time to some like out Hilbert space. And people say, well, this defines some map between my in and my out Hilbert space, which I call the S matrix. And so, well, I'm not going to write down the Moeller operators. You've seen that before. But for massless particles, the story is more complicated. In particular, it's more complicated because this free time evolution is not the right prescription. And one can show that, in fact, the Moeller operator, if we define it like essentially so the action of the Moeller operator And so this prescription does not converge. If H was like a free theory, then again we would get 1 and everything would be fine. But here, so the asymptotic behavior of my full Hamiltonian and my free Hamiltonian for, say, QED in 4 dimensions is such that this expression here on the right-hand side actually doesn't make any sense. And right, so I'm going to talk about this. So there's like a bunch of subtleties. One of them is that we really want to replace H by an asymptotic Hamiltonian, which is better in capturing the asymptotic behavior of our free Hamiltonian, with the overall aim to kind of understand what is the right Hilbert space for scattering with massless particles. And as already mentioned, it's not the Fock space. So why is this interesting? I think there's sort of like a couple of reasons why this might be interesting. First of all, generally understanding the S matrix is great. It's, when we want to do quantum gravity, for example, the only really good object we have. And just to stay sort of at the topic of quantum gravity, one might hope that if we want to develop, say, some notion of flat space holography, there should be some mappings between the Hilbert space of a dual theory and the Hilbert space in flat space. So first thing to do is obviously to understand the flat space Hilbert space. Okay.
May I just,
Yeah.
curiosity.
Sure.
I think Matt made a stronger statement. He said that this doesn't make sense.
Right.
Regardless
So
of-
right. So
Any
it.
comments on that?
Yeah. So I don't know if we should, if this doesn't make sense at all is correct. What's certainly true, this is not a unitary operator. That's essentially Harks theorem. Now, the reason for Harks theorem is mostly in the UV, and here I'm just kind of concerned about IR issues. But it also we'll see that just focusing on Fock space and on unitary operators on Fock space is not the right thing to do, even just like for standard QED in the low energy limit. But we need more general representations of the commutation relations.
Or would you say massive factor?
Right, you would have the same problem. This is not defined, but this is a purely UV problem. And I'm not going to talk about the UV.
It's a purely UV problem now.
Well, I mean, yeah, I'm happy to talk about Harks theorem later. Okay, so let me just give you another quick review of IR divergences. So let's just consider some scattering. Say in QED, we have massive particles coming in and going out. And we can look at processes where one of the outgoing charged particles emits a photon, say, and there's something called Weinberg soft theorems, which tell us that if we are looking at the amplitude of the emission of some photon with momentum k, that this goes with a soft factor, and in particular, what we see is that as the momentum, so k is on shell, as the momentum gets small, wavelength gets big, this right side here blows up. And in other words, the statement essentially is that if we calculate probabilities, the probability of finding some soft particle in the scattering process is infinity. And that's, of course, seemingly nonsense. But the first thing to realize here is that really this here could be a purely tree-level process. So the fact that we get these divergences here is not really like a quantum field theory problem, but it's technically a purely classical problem. Okay. And then secondly, there's a related problem, like a related IR divergence problem, which comes from loops in the quantum calculation. So consider this scattering amplitude where I take some charged particles, scatter to other charged particles without additional photons, say, and I want to calculate a one loop correction to it. And just for fun, I pick this loop. Then one can calculate the loop diagram fairly easily, right? We're just interested, say, in the low energy long wavelength limit of this, and the relevant part here, sort of like the photon propagator, and then the propagator is coming from these two parts. And if we're just like super naive and count the case here, or if we actually do the integral in the complex plane for k0, then we see that this here gives a log divergence, and so needs to be regulated. So this is sort of like something like log lambda. Okay. Now the issue here is that this is a process at order e squared, and all these diagrams at higher loop order come with additional loops, which might have IR divergences. And so our effective coupling is not really e squared, but it's log lambda e squared. And for a low IR cutoff, perturbation theory stops making sense. And what we want to do is we want to resum all these IR divergences. And then we get to what is also already mentioned by Matt, that if I resum all these divergences, what I get is essentially this is lambda to some positive power. So if I send lambda to 0, or it's a log divergence, so maybe let me write e to the number times log lambda. And if I send lambda to 0, this expression goes to 0. So it seems like all the S matrix elements vanish. Now the textbook solution is usually we sum over the emission of some arbitrary additional amount of soft radiation of this form. So we attach like more lines to external and internal legs and say this is all emitted. We have some detector of some finite threshold. And so we say below a certain experimental cutoff, we cannot detect this radiation and should really ask for the inclusive cross-section. And then we can show that this result is finite. Okay. But then the problem still is that the S matrix, so this gives a result for cross-sections or scattering probabilities, but the S matrix itself remains ill-defined. And sort of one thing to realize here is that really this result, that this S matrix elements are all 0, is in fact the correct result. So QED really doesn't have a problem with massless particles, but we're just asking the wrong question here. One way of seeing this is if we scatter massive particles with some charge, we give them a lot of time, then Bremsstrahlung is produced. And if you like open Jackson, you see that the spectrum for Bremsstrahlung behaves somehow like in the short wavelength or higher energy regime, but it approaches the finite energy for very long wavelength radiation. And if we just use high school quantum mechanics and look at what's the number of photons sort of in the low-lying modes, we see that as the energy of our emitted radiation over omega h bar. Well, if this goes positive, if this stays constant as we send omega to 0, then the number blows up, and we have an infinite number of photons emitted in low-lying modes. And this explains why this is in fact 0, because here what we usually do is we take the S matrix element between Fock space states. Fock space states only make sense if we talk about a finite number of particles. So it is really true that the S matrix element between any two states which contain a finite number of particles is 0, and we sort of like need to do better and go on and consider the S matrix elements between states which can contain an infinite number of particles. Okay. So, and one way of doing this has been discussed in the literature, and I sort of agree that the literature is quite confusing and also probably not always correct. Dressed states or coherent states. Apart from Chung and Faddeev-Coolidge, there's also a nice series of papers by Kibble, which discuss sort of how to define these stress states properly. Now, how do dress states work? Let's consider just like a classical problem. We saw that sort of like this divergence here is already classical divergence. We emit an infinite number of photons, or like, well, semi-classical, I guess I should say. So maybe we can sort of understand this already classically and try to solve our problem classically. And one thing one can just calculate is consider classically particle with momentum p, particle scatters off of some potential into a particle with momentum p prime. And what we see is that after the scattering event, some radiation is created, and the radiation can be described by some vector potential. And here, sort of the interesting or important part is that this vector potential consists of two pieces. And one piece depends on the incoming momentum, and the other piece depends on the outgoing momentum. Okay, so this sort of suggests that, well, what we could do is we say, well, P doesn't scatter, like quantum mechanically, particle with momentum P doesn't scatter into a particle with momentum P prime, but it scatters into a particle with momentum P prime accompanied by a coherent state of radiation, which sort of follows this classical profile. And let me just quickly write this down. And what happens if you calculate what this normalization is supposed to be, then you find exactly, again, what Matt said, that this normalization really is exponential of minus infinity, so it's 0, so you might say, well, this state is ill defined. Now, if we just ignore this for a moment, just to finish sort of the discussion of dress states, well, what typically then does is one splits this coherent state here into its two contributions, one which depends on P prime, one which depends on P, and one dresses particles with momentum P, so an electron, with a coherent state which just depends on this P over P dot K. I call this like an in state, and then I have another out state which contains this P prime part of the radiation and the particle P prime. And then at least formally, I can calculate order by order S matrix elements, and I need to regulate this because of this vanishing normalization, and I can remove the normalization at the end of the day and get finite results. Okay, but yeah, that's a problem insofar as that we really have just moved our infrared divergences from the calculation we did into our states, and the hope is that we can do better. Okay, so, okay, let me skip this. So the rough idea here is that really talking about Fock space states is not enough, but we need a better representation of our canonical commutation relations. Usually in a finite dimensional quantum system, there's only one representation. All representations are unitarily equivalent, but if we're in quantum field theory, we have an infinite number of representations of our canonical commutation relations. And the question is, can we pick the right one here? I'm just quickly going to kind of go through the standard, or one way of constructing the standard Fock representation. Usually how we do this is we take functions in some Hilbert space, and we say that that H is all the functions, or H contains all the functions which are square integrable. And then define some inner product. Which I need for later. And then what we can do is, in order to get the Fock representation, we define coherent state operators. And they formally obey some commutation relation. I'm not going to write all of this. And now if I take functional derivatives with respect to f and g, set f and g to 0, then this line here reproduces my canonical commutation relations for a dagger and a. Okay, so this is the standard Fock space representation. Now the question is, can we get other representations? And that's been done in the 60s, I believe, by Clauder, McKenna, and Woods, and has been sort of like absorbed into the physics literature by Kibble. And the idea here is, okay, that instead of using the set of square integral functions, we consider functions which have a somewhat better infrared behavior. So here we see it right, yeah. So we see at very low, at small k here, really we require that they integrate against 1 over k square, or integrable against 1 over k square in the infrared. And there's a dual vector space, dual with respect to this inner product, which is essentially the same expression, except that here we flip k and k plus 1. And these are essentially functions which have a worse IR behavior. Now, the important observation is that this set of functions is still dense in the standard Fock space, and we can sort of use this, choose a basis for this space, and use multiply basis elements by creation operators, and use this as sort of like act with these creation operators on our Hilbert space to build it up. But the second space down there with the ill-behaved functions is, sorry, okay. So, right. So what we can do now is, so these here define our, okay, these here define our wave functions. They have a good IR behavior, and now we can actually use them to act on states of the form. Okay. To act on states of the form, let's call this H. Zeros are formally states of this form, where this H here are these sort of more R-divergent functions. Now, these more R-divergent functions are precisely the class we need, because these are the expressions I've essentially just erased, or this f in here, the p over k dot p, our class are in this class of, in this dual space here. And so, at least formally, we can define this object where W would have a divergent normalization, and then use A's of these wave functions to act on this state and get always finite results. Now, you might argue that, well, but this state here is still not well defined. There's a divergent normalization. However, there's a construction called von Neumann spaces, which I won't go into, which essentially allow you to make this construction here mathematically well defined. So what these are von Neumann spaces is a non-separable Hilbert space, which splits into separable subsectors. So a big Hilbert space and different separable subsectors which are as big as Fock space. And essentially all these subsectors here contain states which differ by a finite amount of, since we talk about photons, radiation. Okay. So 6. Okay, so this is just to hopefully make it mathematically more palatable. We can define formally these coherent states, which, if we consider them as states in Fock space, have a divergent normalization, and we can define creation annihilation operators, which legally can act on these states, and everything's finite. Yeah.
Is the physics of this? Sorry, you said this thing is divergent.
Right. Okay, so I'll talk about the physics in a split second, but let me just mention here. So the physics of the normalization vanishing in this kind of like naive picture of Fock space is really, I have an infinite number of particles, that's not allowed in Fock space. So now the question sort of is, I guess that's what you're getting at, what are these states, these dressed states? Okay. Let me see if I maybe. Yeah, okay. Maybe let me answer this question right now. No. Let me quickly go to the definition of the S matrix so I have everything at my disposal to explain this. So now, how do we define the S matrix? Similar to what Matt said, what we really want is a definition where we take our S matrix and don't evolve. So we want something like e to the minus IH asymptotic T prime e to the H T prime minus T prime prime. And then we want to send the times to plus and minus infinity. Okay. Now the question is, what is the correct asymptotic Hamiltonian? And one way of doing this, and a nice way of sort of like seeing what it should be, is to go to Coulomb Quantization and just look at the interaction Hamiltonian and modify it a bit to sort of like remove everything that's annoying. So schematically, in Coulomb quantization, this is my my interaction Hamiltonian. And what I do is I normal order my current operator. I sort of take this delete all, and from here delete all pair creation or pair annihilation terms so that J really sort of like the number operator along a certain direction, and only keep terms small in momentum. So I obviously need to rewrite this in momentum. Now for the current, if I do this just for the current, this gives me what I call an asymptotic current, which is simply the velocity times the density along a certain momentum. And, well, my asymptotic Hamiltonian then is just this plugged into here and take the, and only consider low modes and ignore back reaction. Okay, now the whole point is that I can, in this expression here, I can insert ones, and again e to the minus h naught t, e to the plus I h naught t, and then bring this into the interaction picture. And then this term in the middle here becomes my standard S matrix, and the terms here on the sides become some operators I call U, or I think Matt called them asymptotic molar operators. And they can be calculated explicitly. And they take the following form. In the end, I want to evolve, say, from time minus infinity to 0. Okay, and then comes the physics. Okay, and this here is. Okay, so there's some, right. So there's some sort of like asymptotic interaction and some phase vector. Now, if we look at the interaction Hamiltonian, this here sort of like known as the Coulomb phase term, and what it essentially does is it tells you, well, if you have one particle in the Coulomb field of another particle, and essentially that's this term modulo one thing, namely that what I did here, okay, maybe, right, so this is, maybe I should write this. So this is the time-ordered version of the asymptotic Hamiltonian. Now, due to the time ordering, this phase here changes, and instead of just the phase of one particle in the Coulomb field of another particle, it's really the phase or the energy of one particle in the boosted version of the field of the other particle. So if I have particles moving at different speeds, of course, they won't have the Coulomb field around them, but some boosted version, and that's captured in here. And this term here, the VAS, is an integral okay, so this is a kind of interesting time evolution here. Namely, one part of the time evolution looks just like an on-shell photon part, and the other one has a phase E, V of the particle P, which is sort of like measured by this current, times the photon's 3 momentum times T. Okay, now, what is this good for? One thing we can do is we can define a dressed state simply by acting with this U on some standard Fock space in state and my photon momentum. And then what I can do is I can calculate, say, the expectation value in this state of my 4-vector potential. Okay. So just to recap, I have a state, I've dressed it with this operator, which creates a coherent state of photons in this very peculiar way. And what you see here, what the result will be, this is the classical electrical field at long wavelength, of course, because we just focus on long wavelength, created by a particle moving with momentum p. Okay. So instead of just, yeah. Yes, this is an operator. Yeah. Okay, so what these states here are not only electrons, but they're essentially electrons with the electric field at very long wavelengths. Now, this doesn't solve the IR problem, because the IR problem sort of is solved by the emission and absorption of additional radiation. And what we can do, we can define sort of like additional operator which creates radiation as a coherent state operator, which creates, so for saying particles Q and P, which creates radiation particle P for the particle P and radiation for the particle Q, where this here is times some function which goes to 1 as k goes to 0. Okay, and we can additionally dress those states with this X-ray radiation. I will call those states here P with a subscript P, because I just have a particle with momentum P and dress it with its own electric field. And we can define a particle with a subscript Q as Q with, so this W is just the old dressing times the radiation dressing. Okay. Okay, so what we have is a bunch of particles which have in their background soft radiation through this R, and then also long wavelength modes which are sort of coherent states to represent their own electric field. Now what you can show, and that's sort of like the bottom line of all of this complicated construction, that these states that the S matrix, the dressed S matrix as defined before, between states, say P and Q, with the same little subscript here, are all finite, that all these states live in the same representation of your canonical commutation relations, which is not the Fock representation, but which is one of these representations which organize themselves in a von Neumann space. And right, so that essentially this object is mathematically well defined. Okay, that was a bit confusing probably. But right, yeah, just to sort of like iterate the main point here once more, we define a dressed S matrix by picking an asymptotic Hamiltonian, which is sort of defined as the relevant terms at low wavelength from the interaction Hamiltonian. If we define our states by dressing with the interaction Hamiltonian, just by acting with the time-ordered interaction picture, sort of like time evolution in the asymptotic region on our states, we turn a Fock space photon into a state in some other representation which contains a coherent state, which if we take the expectation value of the 4-vector potential, gives the correct 4-vector potential at long wavelengths. Now, for different states, all these dressed states which live in different representations of the canonical commutation relations, but it just so happens that if we add the right radiation to make them live in the same representations, we also cancel the IR divergences, or the other way around. If we add the right radiation to cancel the IR divergences, all these states live in the same representation. Okay, so I'm just going to say a few more words in the end why one might think this is sort of like a reasonable thing to do. And it reproduces a bunch of properties that have been found in the like 60s, 70s, and 80s in the mathematical physics literature, and are not very well appreciated, I think. Okay, so we have this huge state of possible representations, and in those are these IR representations I've constructed. And these representations, so I've just shown that I can define an addressed S matrix which acts as a unitary operator on one of these single representations. What that means, in other words, is there are selection sectors in QED which are given by those different representations. So if I take a superposition of states in one selection sector, it will always scatter to the same selection sectors. In fact, what one can show is that these superselection sectors, which have been found recently by Andy Strominger and friends, are precisely those representations here. Right. Generally, the states we constructed here, they take the following form in like sort of like a semi-classically idealized picture. They come with some radiation attached. And before the scattering, there's the correct boosted Coulomb field around the particle. And after the scattering, there's again the correct different boosted Coulomb field around the particle with its new momentum. Then there's a quite interesting result from 1963 or so by Schwartz, who said that normalized states in QED, or QED doesn't contain particles, but only contains infraparticles, which means that normalized states don't live on the mass shell. And here it's kind of like easy to see how this comes about. Namely, those states here, which live in one of these superselection sectors, always contain some amount of radiation, which I had to sort of like add by hand to make them live in the same representation. If I build a superposition, so if I actually build not a delta function normalized state, but a proper normalized state, then each of these states must contain some amount of radiation, and so cannot live on the mass shell. And then lastly, what's hopefully also clear is that this choice of representation breaks Lorentz invariance, and this is also an established fact that for massless particles in 4 dimensions, a choice of representation will break Lorentz invariance, essentially because if I, say, take a particle where I don't add additional radiation, take all the other particles in the same superselection sector which need to contain radiation, and I boost this, then suddenly I have a particle with a different momentum which does not contain radiation. But this state didn't live in the previous superselection sector, but lives in a different superselection sector. So really Lorentz transformations take you between different representations. Okay, yeah, I think that's it's time for lunch. Yeah.
Is it the same as matrix?
Oh, yes, yeah. So what it really boils down to in the end is the following. My S matrix, my dress S matrix, is my asymptotic time evolution times my standard S matrix times my asymptotic time evolution. These dress states here take the form, essentially, formally, Fock space state times asymptotic time evolution, potentially times radiation. So if I take the S matrix over between this state and this S matrix, the asymptotic time evolution essentially cancels. And what I really have is a calculation where I have coherent states, like Fock space states stressed by coherent states acting on the S matrix, and that at least perturbatively is sort of like the old calculation by Chung and other people. So this is the standard S matrix, but not between Fock space states, but between states with coherent radiation.
I mean, but as Matt said, this was a definition, but nobody really computed this S matrix to see what was coming out. I mean, if we're going to be pragmatic and see what is the actual scattering not to be able to.
Well, I mean, you definitely can, like perturbative, you can definitely do these calculations, and they have been done. So you can write down what these states are. You can do the standard S matrix calculation perturbatively, order by order. Like just order by order calculations? Like Chung's paper? Of course, yeah.
There's no expression for S matrix. It does not give an answer. It doesn't tell you UV cutoff is. It doesn't explain momentum conservation. It doesn't have any actual answers. All it talks about is the divergence example. It doesn't actually tell you what the S matrix is.
Well, but so the S matrix here, and this is just a perturbative expansion e to the sort of interaction Hamiltonian, right?
What is this? S matrix equals something on the right hand side.
Sorry, S matrix equals something?
What is the, just calculate it in some specific case. Because you need to put cutoffs in, you need to deal with momentum conservation. None of the Chunga skills, any of these things. It's kind of foolish, kibble, right?
Well, maybe we can talk about this later, but I disagree.
Okay, it seems that we have a lot of discussion for lunch, so let's just find Dominik again. Yeah, because this is really the drama of this what is the actual
Right.
Moreover, it will depend on the factor parameter, right? It's scale of separation.
Oh, right. So I mean, you can put a scale separation. You would put this in the radiation if you wanted to, but this is sort of a choice of actual scattering state. And here for the dressing of the field, there I actually don't know. So,
Tell me what the second.
I mean,
Tell me what the second. There were one loop or whatever.
There's some ambiguity.
All anyone ever does is show that the self-singularity cancels.
I mean, so here, like the estimate
I was told
just the time order is like exponential over the actual
Calculate. Something like calculation. I'm saying once you try to calculate it, it gets much more complicated. So write it down and it's beautiful. Then you actually get into it's really, really dirty.
But how
So
can
you have an S matrix that doesn't
So for me,
I mean, you don't even scatter one time, right?
What do you tell me when you scatter? You just get
Not trivial thing.
Right, but I'm